Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called enterprise-wide optimization, advanced analytics solutions, water consumption minimization and industrial complexes. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Water consumption minimization in industrial complexes. Saving and using water in industrial complexes. We can save water in industries by raising awareness among employees, measuring water consumption, optimal water use, waste recycling, installing water-saving equipment, routine pipe checks, etc. Only 3% of the water on Earth is pure and can be used for daily routine. In 1999, between 5 and 10% were consumed for industrial purposes. As the world's population grows, water consumption will also grow. By 2030 it can reach up to 20%, so it is necessary to raise awareness about ways to save water in industries by reducing their consumption. In addition, it will help the company reduce its water bills. Normally, in standard industry, water is used for the cooling of plants and equipment, the cleaning and preparation of products, cooling, and the application of paint and stains to the product. But there are industrial processes, intensive in the use of water, such as the production of shale gas. Wastewater treatment plants. The major aim of wastewater treatment is to remove as much of the suspended solids as possible, before the remaining water, called effluent, is discharged back to the environment. As solid material decays, it uses up oxygen, which is needed by the plants and animals living in the water. Primary treatment removes about 60% of suspended solids from wastewater. This treatment also involves aerating, stirring up, the wastewater, to put oxygen back in. Secondary treatment removes more than 90% of suspended solids. Saving and using water in industrial complexes through economic optimization. Analysis of water networks whose application can help to reduce the consumption of fresh water, first use, reduce wastewater generation, reduce water costs, determine the investment needed to achieve a specific goal. Use of advanced decision-making artificial intelligence to identify the best opportunity to reuse of currents, regeneration, and treatment. In addition to the benefit of saving this scarce and valuable natural resource for the humanity. This section is based on the presentation made by the engineer Elva Arzade at a workshop on optimization in the oil industry, held in Oaxaca in 2011. The name of the presentation was Software of Instituto Mexicano del Petróleo, IMP, for Water Consumption Minimization in Gas Complexes and Refineries. This section is based on the presentation made by the engineer Elva Arzade in the Advanced Optimization Techniques for the Petroleum Sector workshop, in Ciudad de Mexico, in 2016. The name of the presentation was AGRD, Water Network Optimizer for Industrial Complexes. 2/3 of the surface of Mexico is in the arid zone in the world. AGRD is the IMP software for the minimization of water consumption in gas complexes and refineries. His goals are decrease water consumption, cooling systems, steam generation system, other industrial services, and efficient water management. Mathematical modeling. Water sources. Rivers and aquifers in the area, clean water treatment prior to discharge, and stormwater reuse. Process. Pre-treatment, cooling towers, industrial processes, existing treatments, new treatments, and discharge management. The features of the mathematical model are non-convex nonlinear problem, then several local optimum solutions exists. Global solvers, or special multi-problem optimization algorithms, are required. Local NLP solvers usually may fail to find feasible solution. For effective global optimization is required tight bounds for flows and concentrations, and special cut, overall mass balance for each pollutant. The diagram shows the streams with the possibility of reuse in a refinery. The diagram shows the superstructure of the water network used in this case. The four major steps of the superstructure are: units balance, water source to water discharge reuse, process to process regeneration, process to treatment to process, or process to treatment to process, and recycle. Water source to water discharge to water source. The diagram shows the refinery organized into areas according to the processing of the water. These are pre-treatment, processes, and treatments, sources and pre-treatment parameters. The natural water sources are river water, water well, and pluvial lagoons. These sources require a bleaching process to be used. The pre-treatment water sources are purge collector and rinse collector. These sources require the use of a filtration, or an ion exchange process. The parameters of the sources are physic-chemical composition, maximum flow, and minimum flow. The parameters of the pretreatment are components removal in percent, maximum flow, and permanent services. Process parameters. The parameters of filtration and ionic exchange units are removal in percent, and weigh. The parameters of destination processes are concentration cycles and flow. The table shows a summary of water treatment technologies, characterized by some of their parameters. The loss of water is not considered at the entrance/exit of treatments. The treatment for producing demineralized water consists of 1 unit per each discharge. Ultra-pure water, highly salted purge, and lowly salted purge. Discharge management. The goal is that the discharge is within the maximum allowable limits. The basic technologies are primary and secondary existent treatment, highly salted purge segregation, pluvial capture, and new treatments. Flow balance equations. Sources total flow, mixers entrance, exit splitters, processes with one stream, entrance to treatments, exit from treatment, and discharge flow. To analyze the performance of the mathematical model, 2 cases were studied. Case A. Improved removal of fats, oils and phenols in the treatment of sour water plants, determining the savings of fresh water using this water as desalted water. Case B. Reuse of water between the various refinery processes, quantifying the decrease in consumption of fresh water, by using this oily water. Case Study A. Improved removal of fats and oils and phenols in free sulfuric acid water. The image shows the water savings in Case A. Case Study B. Reuse between processes. The image shows reuse of water in the Case B. A comparison of the results of the 3 cases, the base, and the A and B, allows us to conclude. The use of tar, an external water treatment plant that is expensive, has been virtually eliminated. The Case B, reuse water between processes, has the best performance when compared to Case A, improved removal of fats, oils and phenols in sulfuric acid-free water. The environmental impact of water reuse is significant, as it saves 9.4% compared to Case A. It is clear that the mathematical model brings economic and environmental benefits to the refinery. Another aspect of analysis was the comparison of mathematical methodologies, 2 of which were analyzed: mathematical programming, and pinch analysis. Pinch analysis is a methodology for minimizing energy consumption of chemical processes by calculating thermodynamically feasible energy targets, or minimum energy consumption, and achieving them by optimizing heat recovery systems, energy supply methods, and process operating conditions. The 2 methodologies produce similar results, but the approaches are different. Mathematical programming uses more water treatment processes, pinch analysis more water reuse. The software for water management implements NLP model, and pinch analysis. Discharges to the environment meet specifications, eliminate bottlenecks in treatment units, reduce capital costs of new treatments, and reduce costs of fresh water supply, treatment and discharge. The computational results are: the CONOP solver could not find feasible solution, and therefore no experiments were conducted with this algorithm. The table presents the computational performance of the global Barron algorithm. This section is based on the document Global Superstructure Optimization for the Design of Integrated Process Water Networks. It contains the detailed mathematical formulation used in Agua Red. Amatovic and Grossman propose a general superstructure and for the global optimization for integrated process water networks. The superstructure consists of multiple sources of water, water-using processes, wastewater treatment, and pre-treatment operations. Unique features are that all feasible interconnections are considered between them, and multiple sources of water can be used. The proposed model is formulated as a nonlinear programming (NLP) and as a mixed integer nonlinear programming (MINP) problem, for the case when 0 to 1 variables are included for the cost of piping, and to establish optimal trade-offs between cost and network complexity. To effectively solve the NLP and MINP models to global optimality, Amatovic and Grossman propose tight bounds on the variables, which are expressed as general equations. They also incorporate the cut proposed by Carupia and Grossman, to significantly improve the strength of the lower bound for the global optimum. Generalized superstructure for the design of integrated process water networks. The proposed model of the integrated water network is based on the given superstructure. The superstructure, which is an extension and generalization of that given by Carupia and Grossman, it consists of one or more water sources of different quality, water use processes, and wastewater treatment operations. The unique feature is that all feasible connections between them are considered, including water reuse, water regeneration and reuse, water regeneration recycling, local recycling around process and treatment units, and pre-treatment of feedwater streams. The multiple water sources include water of different quality that can be used in various operations and can first be sent for pre-treatment. The superstructure incorporates both mass transfer and non-mass transfer operations. In mass transfer process operations there is direct contact, usually countercurrent, between a contaminant-rich process stream and a pollutant-poor water stream. These units can be represented as true pollutant-rich process streams. In this case, during the mass transfer process, pollutant loads are transferred from the process streams to the water. The concentration of pollutants in the process stream is reduced, while the concentration of pollutants in the water stream increases. In many processes, there is a loss of water that cannot be reused in a water-using operation. This unit represents a unit of water demand or a water sink. Cooling towers are typical process units in which water is lost through evaporation. From some operations that use water, the water is available for reuse in other operations. These units represent water sources. Accordingly, the superstructure can be used to represent separate subsystems as well as an integrated total system. The mathematical model of integrated process water networks consists of mass balance equations for water and the contaminants for every unit in the network. The model is formulated as a non-convex NLP, and as a non-convex mixed integer nonlinear programming, MINP, for the case when binary variables are included to model the cost of piping or selection of technologies for treatment. The nonlinearities in the models appear in the mass balance equations in the form of bilinear terms, concentration times flow rate. In addition to this, nonlinearities appear in the objective function as concave terms of the cost functions for the water treatment operations. Hence, the water network models are non-convex, and in most cases lead to multiple local solutions, making it difficult to obtain the global, or a near-global optimal solution. The basic options of the proposed water network optimization model are given as follows. First, the model enables the choice of a single or multiple sources of water that are available for the network plant operation. Second, water sources can be clean water without contaminants, or water with multiple contaminants. Water with higher quality is more expensive, and the total cost will be minimized at the expense of lower quality water. Water with contaminants may be sent directly to treatment units, before using it for water-using operations. Third, the water network can consist only of water-using operations or wastewater treatment operations. In addition, it can be an integrated water network including both water-using operations and wastewater treatment operations. Fourth, all feasible interconnections are possible in the network for every option mentioned before. Fifth, it is possible to choose local recycling around the water-using operations or the wastewater treatment operations. Local recycling can be used to satisfy the flow rate constraints, and, in these cases, it is possible to have an additional reduction in water consumption. Sixth, industrial water network systems usually consist of different types of water-using operations that can be classified as mass transfer operations and non-mass transfer operations. Both types of these operations are included in the superstructure, and seventh, in many processes, there is loss of water that is not available for reuse in a water-using operation. Hence, this unit involves the water demand unit, and is a water sink. Moreover, from some water-using operations water is available for reuse in other operations, and they represent sources of water. In all the options, the number of contaminants, water sources, water-using operations, and wastewater treatment operations is fixed. To make the model more general, we also address the class of water network problems when the flow rate through process units is a continuous variable. It should be mentioned that in this case the feasible space is increased, and several additional bilinear terms are added to the model, for the water-using process units, which increase the computational requirements. The proposed model enables modeling and optimization of any of the options of the water network superstructure. In the next section, the MINLP model for the superstructure showed previously is presented. It should be noted that this MINLP can be reduced to an NLP when binary variables, and corresponding mixed integer and integer constraints are not included. The mathematical model is presented in its entirety, but only the content of the images is described. You can pause the video to take a closer look at the algebraic formulation. Initial splitters. The feed water of an initial splitter SIS for freshwater source S, it can be clean water without contaminants, or water with single or multiple contaminants. Freshwater from the initial splitter can be directed to the mixer process unit, the mixer treatment unit, the mixer demand units, or the final mixer. Mixer process units. The mixer process unit MPUP consists of a set of inlet streams from the splitter source unit, the splitter treatment unit, the initial splitter, and the splitter process unit. An outlet stream from the mixer process unit is directed to the process unit. Process units. The PUP process unit consists of an input current FPU and P, from the mixer process unit, and an FPU output from the process unit. The inlet and outlet water flow rates of the process unit are equal. The overall material and mass balance equations are included for each pollutant J. Splitter process units. The splitter process unit SPUP consists of an inlet stream from the process unit, and a set of outlet streams directed to the final mixer, the mixer treatment unit, the mixer demand unit, and the mixer process unit. Demand and source process units. The demand process unit is shown in figure. The mixer demand unit MDUD unit consists of a set of inlet streams, from the splitter treatment unit, the splitter source unit, initial splitter, and the splitter process unit. An outlet stream from the mixer demand unit is directed to the demand unit. Mixer treatment units. The mixer treatment unit MTUT consists of a set of inlet streams from the splitter source unit, the initial splitter, the splitter process unit, and the splitter treatment unit. Treatment units. The treatment unit 2T consists of an inlet stream from the mixer treatment unit, and an outlet stream from the treatment unit. Splitter treatment units. The splitter treatment unit STUT consists of an inlet stream from the treatment unit, and a set of outlet streams directed to the mixer demand unit, the mixer process unit, the final mixer, and the mixer treatment unit. Final mixer? The final mixer unit MF consists of a set of inlet streams, from the initial splitter, the splitter process unit, the splitter treatment unit, and the splitter source unit. Objective function of the NLP. The objective function of the NLP water network problem can be formulated to minimize the total consumption of fresh water, for the operation of the network plant, and the total amount of treated wastewater, in the treatment operations for an integrated system. Objective function of the MIN-LP. Here, C water is the yearly cost of water for the network plant operation, IC treatment is the investment cost for treatment units, OC treatment is the yearly operating cost for treatment units. The MIN-LP considers binary variables with their corresponding lower and upper bound constraints. The objective function for the MIN-LP model is to minimize the total network cost, which includes the cost of the network piping, concave function of the flow rate with fixed charge, and the cost of water pumping through pipes, linear function of the flow rate. Here, C. Water is the yearly cost of water for the network plant operation. IC. Treatment is the investment cost for treatment units. OC. Treatment is the yearly operating cost for treatment units. OC. Pumping is the yearly operating cost for pumping water through pipes in the network, under the assumption that the pressure drop in each pipe section is fixed, and IC. Pipes is the investment cost of the pipes in the network. Notice that concave cost functions are involved in equations 46b and 46e, which are additional sources of nonconvexities to the bilinearities in the mixer equations 7, 19, 27, and 38. Optimal design of water networks for shale gas hydraulic fracturing. This section is based on the document Optimal Design of Water Networks for Shale Gas Hydraulic Fracturing, including economic and environmental criteria. Location of the potential shale gas reserves according to studies by Pemex. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." The importance of this phrase lies in the fact that all modern mathematics is based on algebraic models that become algorithms, that use all the power of current computer technologies. Thank you for your attention.